We call that discrete random variables are the ones that take values like 0, 1, 2, 3, 4 that involve counting, countably many values. Then there's the other random variables that behave kind of like choosing a point inside of a region in the plane. Those are called continuous random variables. Now it's time to look more closely at those. So we call a random variable continuous if it takes real values, not necessarily all real values, but at least some real values. And if we can express the probability, let's say random variable x, the probability that x is between a and b as an area of one region in the plane over area of another bigger region in the plane. So for example, we have the exponential random variables. So this satisfies, if we have an exponential random variable with parameter lambda, this satisfies the probability that y is greater than or equal to b equals e to the negative lambda b. So that means the probability that y is between a and b equals the probability that, technically, this is a strict inequality, y is greater than b. So the probability that y is between a and b, not including a, is the probability that y is greater than a minus the probability that y is greater than b, which apparently equals e to the minus lambda a minus e to the minus lambda b. Alright, and the question is, what regions in the plane create the required fraction? We're supposed to have area over area. And the answer is the numerator and denominator are the integral of lambda e to the minus lambda x dx from a to b, and the integral from 0 to infinity of lambda e to the minus lambda x dx. So this area under a curve and this area under a curve. So the bigger area is from 0 to infinity, something like that, and then the smaller area is just from a to b. So shaded area over all the area under the curve. And this is because if we integrate lambda e to the minus lambda x dx, we get, let's see, I kind of wish I had a minus lambda next to dx, so I'll put it there. E to the minus lambda x minus lambda dx. I had to introduce a minus sign, so I'll put minus on the outside. And then that's minus e to the minus lambda x plus c. So the numerator is minus e to the minus lambda b minus negative e to the minus lambda a, just evaluating that from a to b. And the denominator is, well, we found out in a previous lesson that that's 1. We did an indefinite integral in an earlier lesson. So what's on top is e to the minus lambda a minus e to the minus lambda b, exactly what we wanted. It's kind of nice that we have 1 on the bottom because we don't actually have to divide by anything. In fact, we almost always work with a smaller region inside of a larger region that has area 1. So we have a smaller region inside larger region of area 1. So the probability is just equal to the area of the smaller region. We don't need to divide by 1. Just like here. And that smaller region is often the region between a positive function and the x-axis. Actually, both regions. Let's call a function f of x a probability density function. If it satisfies 2 properties. First of all, it's greater than or equal to 0. Second of all, the integral from negative infinity to infinity of f of x dx equals 1. So that means that we can use the area under the curve and above the x-axis to be the big region, and then we can cut it up into pieces and use one of those pieces as the smaller region. So we use this as follows. First of all, we choose a point between the curve and the x-axis. Then we let capital X be the x-coordinate of that point. Then the probability that x is between a and b is the integral from a to b of that function f of x. All right, now before I was careful to say strictly less than, and now I'm not being careful. I'm just saying less than or equal to. So I have to admit what's going on here. Why am I not being so careful with less than or equal to versus less than now? So, well, the thing is that if we take the area of a region, what I'm gaining or losing by using less than or equal to is the boundary. So we have some curve f of x. This is the x-axis, and here's a and b. So if we look at the area between a and b, it's really the same with or without either end boundary. I could also say, I guess, that the area of just this boundary here the segment has area 0. So including it or not including it doesn't make a difference. Since probability is area now, this has an area 0, so we're adding 0 or subtracting 0, it doesn't make a difference. So the exponential probability density function is f of x equals lambda e to the minus lambda x for x greater than or equals 0 and 0 when x is less than 0. So I'm adding this just so that it's defined for all real numbers. So the graph, well, the important part of the graph is here. Sorry, this is x in the exponent, e to the minus lambda x. When x is 0, then that's 1, and lambda times 1 is lambda. So we have this, and then between 0 and negative infinity, that's all 0. So just to put a and b on this graph, So the probability that our random variable is between a and b is the integral from a to b of lambda e to the minus lambda x dx. So it's this region here. All right, now let's look at another curve. So let's ask, is the function f of x equal, so it's given by 0 or 100 over x squared. 0 if x is less than or equal to 100. 100 over x squared if x is greater than 100. Is this a probability density function? Well, it's definitely always positive, because when we plug any number into x squared, whether x is positive or negative, that's positive, and 100 over it is positive. So let's see if the integral, I guess we really only need to integrate from 100 to infinity, because before that it's just the x-axis. So we need to check to see if the integral is equal to 1. So it's greater than or equal to 0. And then the integral is, so the area underneath it is, let's see, from 100 to infinity, 100 over x squared dx, which is the limit as b approaches infinity. That's an improper integral. 100 times the integral of x to the negative 2 dx, integrated from 100 to b. So that's the limit as b goes to infinity of 100 times x to the negative 2. When we integrate it, becomes x to the negative 1 divided by negative 1. Evaluated from 100 to b, which is, so that's 1 over x, negative 1 over x, so negative 100 over x. So the limit as b goes to infinity, negative 100 over x, evaluated from 100 to b. And that is the limit as b goes to infinity of negative 100 over b minus negative 100 over 100. So that's 1, and then as b goes to infinity, this goes to 0. So it's 1. So yes, it is a probability density function. All right, now let's do a probability problem with it, since it's a probability density function. So let's choose 5 points at random under this curve. Choose 5 points at random under the curve, and by under the curve I mean and above the x-axis. Now I ask, what is the probability that 2 of the 5 lie to the left of the line x equals 150. So there's a vertical line, x equals 150. All right, so this is a binomial experiment on top of the continuous random variable. We're going to do something 5 times and ask what's the probability that we get a success 2 times. And our function is 0 for x less than or equal to 100, 100 over x squared for x greater than 100. So if we want the probability of, let's say, 1 point first, just to keep it simple. 1 point lying to the left of x equals 150. So 100 over x squared looks something like that. And we got 150 here. So I guess we're going to integrate from 100 to 150 and find that area there, because the whole area under this curve is 1. So the probability that each point individually lies between x equals 100 and x equals 150, so the shaded region there, is the integral from 100 to 150, 100 over x squared dx. All right, we said that that's negative 100 over x evaluated from from 100 to 150. So it's negative 100 over 150 minus negative 100 over 100, which is 1 minus 2/3, which is 1/3. All right, so our probability of success is 1/3. And we're looking for 2 successes out of 5. So 5, choose 2 of them to be the successes. Each success happens with probability 1/3, and each failure happens with probability 2/3. All right, now in addition to the 2 defining properties of probability density function, there's 2 more properties that we really should pay attention to. So in addition to the defining properties, of a probability density function, so that is f of x has to be non-negative, and the integral from negative infinity to infinity has to be 1. So we have 2 more which are, let's say, nice to have. Which would be nice to have. One is, since we're integrating this thing whenever we want to compute a probability, it should be easy to integrate. Or it would be nice anyway. And then B, if we're going to actually use this for something to predict some real world phenomenon, this curve should be chosen so that the areas under it accurately reflect our opinion based on historical data. So it should accurately, let's say, model our opinion based on available historical data. All right, now here's where probability starts to get a little bit flaky. So one reason is that no amount of historical data, any data we read, is going to have to be finite. So no finite amount of historical data leads to a smooth curve. Because a smooth curve has infinitely many points on it, and if we only have finitely much data, then we're just not going to have a smooth curve. So we're definitely approximating here. And then the second issue is that sometimes we can't have both A and B. Because some functions, like let's say ordinary exponentials, are easy to integrate but might not be accurate. So something like e to the x is a cinch to integrate. I don't want to erase this. Easy to integrate. I've got a little bit of space left that you can see, but not accurate. And I'll put the other part of number 2 here. Some functions like e to the minus x squared over 2. So you might remember from calculus that we don't have any formulas for integrating exponentials that have an x squared in the exponent. So some functions like this are often accurate, but impossible to integrate. Impossible meaning we do not have a formula for the integral of e to the minus x squared over 2. We could use trapezoid rule or Simpson's rule or something, or use a computer program to do one of those rules and make a table, but that's not something we can integrate by itself at face value. So we will look at both of these later. Functions that are easy to integrate but might not be accurate, and functions that accurately represent something in the world but are not possible to integrate. The end.